Welcome to Unreal Gems. In the last video, we took a look at some basic PBR concepts like base color, roughness, and metallic. In this one, we are going to take a look at some more complex topics, like for example, specular, ambient occlusion, and also normal maps. So I hope that this video clears them up for you. Roll intro. Okay, so we are beginning this video with a special case, which is the specular ping in the Unreal Engine shading model. One may think that that specular ping is prepared to input an specular map from the Specular-Glossiness PBR workflow. But remember, in our case, we are working with metal roughness. In Unreal Engine's case, specular represents some other stuff that we are going to see right now. But remember, it is not, I repeat, it is not the specular map from the Specular-Glossiness workflow. Don't use that, please. Okay, so what is specular in Unreal Engine then? Well, it's a parameter that controls how much specular reflection a surface has. Okay, so for example, for a value of 0, it will be fully non-reflective, but a value of 1 will make it fully reflective. For metallic objects, specular has no effect on the shading model. So the default is 0.5, which is a 4% specular reflection. This will be correct for almost all materials, so just be aware that usually you are not going to be modifying this parameter. So remember that. But if you know what you are doing, you can use it for cavity maps, which provide us with small scale shadowing. So small scale detail will not be picked up by the real-time shadows, and we can gain that small shadows, small detail shadows, using these cavity maps and using the specular parameter. Okay, so that's one way of using it. Another is to control the index of refraction of the material. So as you can see here in this formula, you can calculate based on the index of refraction of the material the specular parameter. So you can input that. You can see the effect that it has here. You can see that for a value of specular of 0, you have no specular reflections, while if you go to 1, you have those specular reflections again. So now that you know what the specular is, just remember that it has nothing to do with the specular map from the Specular-Glossiness PBR workflow. Again, as I mentioned before, usually you will not have to calculate this parameter because the default value works fine for almost all materials. So just remember that. You can calculate it for skin, for metal, for glass, using the index of refraction if you want maximum quality and precision. We will see an example next with the ambient occlusion maps and the cavity maps. So just bear with me. We are not going to see the example now in Engine, but you will see it later. Okay, so next up is the ambient occlusion texture map. This map is common to both workflows, so metal roughness and specular glossiness. Remember that we are using metal roughness, so in this case it is okay to use ambient occlusion maps because they are supported by Unreal Engine. Okay, so what does this ambient occlusion map do? So it is used to calculate how exposed each part of the surface is to light. 0 is going to be occluded, and 1 is going to be exposed to ambient lighting. So you are going to see in crevices or small spaces that you are going to have black in the texture map, and 1 is going to be white, and it's going to be in surfaces that have no geometry around and light can reach easily. You can calculate it in Maya with Arnold, Blender, 3ds Max, or ZBrush. It is quite easy. You just throw out rays from that point of the surface out. If they collide with geometry, it is going to be blocked, and if they don't collide with anything, you are going to assume that a lot of light is going to be able to reach that part of the surface. So this type of map will bring a lot of realism, and it accounts for shadows that we are not going to be able to account for in real-time rendering, because you need small detail shadows that if you calculate them, it's going to be troublesome for performance. So that's why we use these types of maps. You can calculate it in real time, but it is quite less precise. So you can use screen space ambient occlusion or HBAO to calculate this, but as you are going to be able to see, it is not perfect. A ray tracer is going to do a much better job calculating ambient occlusion. Cavity maps are quite similar, but it captures higher frequency detail in the surface. So as you can see, only the smallest of crevices are going to be present in this cavity map, and it is going to help with that self-shadowing of high frequency detail. Again, you can calculate it outside of Unreal and it is going to be quite easy. You just calculate it the same way as the ambient occlusion map, but with smaller maximum ray distances. So parts of the surface are only going to be occluded if they have geometry that is blocking them really close up. That's why you know that it is high frequency detail. Okay, so let's dive into some examples so we can see how the ambient occlusion maps work in-game. So it is quite easy to apply an ambient occlusion map. First things first, we need to go ahead and in the texture check that the sRGB parameter, which by default comes activated, we need to deactivate it. So check that it is disabled. And once it is disabled, we can go ahead and create our material. Since it's quite straightforward, I've already done it for you. It's quite simple. I simplified it and did not include the metallic and roughness maps, so you see it clearly. We have the base color, just so you can see the material, and here we have the ambient occlusion. If you are using static lighting, this is the simplest way to apply ambient occlusion, and it is going to work properly. But if you have movable objects with static lighting, this ping is going to be ignored by Unreal Engine. So you need to be careful, and in those cases, you need to go ahead and use the following shader graph instead of that simple one. In this case, it is quite similar, but not the same. You are going to multiply the base color by the ambient occlusion map. That is going to kill the color where the ambient occlusion map is black. And again, you are going to use the specular value to kill the specular reflections in non-metals. And you just do that using the value of specular that you have already, in this case the default one, 0.5, and you multiply it by the ambient occlusion map. That is going to kill the specular reflections where the ambient occlusion map is 0, which is what we want since there are no specular reflections in crevices in objects. So this is another way. Lastly, I wanted to let you know a little trick. This is also another way in which you can use a cavity map. So you just multiply the cavity map by the base color and the cavity map by the specular value. And that is a way to apply a cavity map in Unreal Engine. You could, of course, combine it with the ambient occlusion ping if it is supported in your desired rendering type, or even combine both maps in this way if you want to. A last way that it's quite simple also is just to disable the static lighting in the project settings and then use everything as movable, and you are going to be able to use the ambient occlusion map just using the ping. So that is another way, disabling static lighting. This is due to Unreal Engine calculating the ambient occlusion result multiplying by the light maps. So if there is an object that has no light maps because it's movable, it doesn't work. So that's the reason behind that not working. Again, we are now going to see a modified material in which I have inputted a lot of parameters so that you can see the difference and we can switch parameters in real time. So I have a material instance in which I can modify everything. So let's go ahead and start with everything disabled. So if we input 1 in every single parameter, this is the same as not having the ambient occlusion map. If I apply it in the base color using 0, you see that in the crevices we have self-shadowing. So the object gains a lot of volume, a lot of contrast, and the render improves quite a lot, as you can see. So I quite like the effect. If I go ahead and also use the specular option, you can see that where the map is black, you don't have the specular reflection. So let me do it in a different way so you can see it better. If I go right here and I use this specular reflection in this angle, you can see that it enters the place where the crevice is. So if I just turn down, you can see that where the crevice is, the specular highlight is going down first. You keep it where the surface is exposed, but where it is not, you can see that the specular highlight will be gone. Again, I recommend using 0 and tuning the ambient occlusion map before Unreal Engine. I just made this material so you can see better how it works. Again, another thing that I forgot to mention is that you need this ambient occlusion way of doing things, because in mobile rendering, the ambient occlusion pin, it is not supported. So this is also not supported in mobile rendering. So just bear that in mind. Okay, so now you may be wondering how it looks with the final material. It is quite easy. You see that we have the original shader graph and we just added the ambient occlusion map multiplied by the base color and multiplied by 0.5, which is the default specular value. So again, you can see the final result with the metallic map also and the roughness map. It is quite easy. Again, I have prepared another material instance so you can see it better. Let's go ahead and disable ambient occlusion, and let's now apply the material instance to our barrel. So this is without ambient occlusion. You can see that things look quite flat. If I go ahead and apply the base color ambient occlusion, you can see that we gain some shadows. If I go further, you can see that in the crevices, you gain self-shadowing. So just take a look at that. It is quite simple. And again, without, you lose those self-shadows. So again, let's leave it at default. Take a look at these shadows right here. We would not have them without the ambient occlusion map. And now the specular. Let's go ahead and enable it using 0. You can see that it kills where the ambient occlusion map is black, and you can see that the specular reflections are being killed where they need to be. Let's go ahead and get another angle, and let's go ahead and exaggerate it so you can see it better. You can see that you are losing them in the place that you want. Here it is not so apparent because the material has variations. We only have specular reflections in other places, and since this is metallic, you are going to have trouble seeing it because specular does not affect the metallic input. So we would need some plastic so you could see it better with the AO applied to the specular. But you can see that it looks quite well, and we gain a lot of volume, a lot of contrast in the object, and the render improves quite a bit in my opinion. So again, these maps are quite underrated, but they give us a lot of shadow detail without any extra cost at all, because it's just multiplying a texture by another texture, as you can see. So it is quite simple to do, quite simple technique, but it is quite powerful and it looks quite good. Okay, so I just finally wanted to show a comparison between a custom AO material on the left for a movable object and a material that just uses the ambient occlusion pin on the right, which is static and uses baked lighting. As you can see, the material is straightforward and the result is almost exactly the same as with our custom AO material. So you can see that or version is working pretty well since the look is quite similar. Okay, so the next kinds of maps are also common to the PBR workflow, and the next one that we are going to take a look at is the normal map. This map is used with the height map to provide detail from a high poly mesh to a low poly mesh. So you can bring extra detail without extra geometry. Okay, so the normal map is quite simple. It brings, as I said before, high definition surface detail from a high poly mesh to a low poly mesh, and it does it by modifying the normals of the mesh depending on the pixel values in the normal map. Each channel in the normal map represents a different surface direction variation in the normal. So depending on the color, each color represents the X, Y, and Z offsets of the normal, the original normal in the surface. You can see that it brings a lot of detail. This is the color map, and this is the color map plus the normal map without extra geometry. Just with this, you can see that it brings a lot of variation and it brings out a lot of detail in the surface. One needs to be careful because there are two formats in the normal maps. One of them is DirectX, is the one that Unreal uses. So if you do have a OpenGL format normal map, you need to do a flip in the green channel in Unreal Engine. We will see it after this, how you can do it. But just remember that if you have an OpenGL type normal map, you need to convert it to DirectX. This can be done inside Unreal. You can tell more or less because if you have the wrong normal map, you're going to see that things look that they go inside instead of outwards. So you can see instead of bumps, valleys, and so on and so forth. One way of recognizing which type of map it is, either DirectX or OpenGL, it's how it looks like it is being lit. In the DirectX one, it looks like it is being lit from the bottom right, as you can see, the light coming from the bottom right. While in the OpenGL format, it looks like it's coming from the top right. Okay, so normal maps are quite simple to use. When you import a normal map, if it has normal in the name, it is automatically going to identify it as a normal map and configure it for you. But just in case, you need to check that everything is all right with the normal map. Remember that we needed to distinguish between OpenGL and DirectX. I have brought an OpenGL normal map so you can see how you can adapt it for it to work with Unreal Engine. So let's go ahead and take a look. I have already imported it. It is just a matter of dragging it from the Windows Explorer. And once you have it in Unreal, if it pops a message right here saying that you imported a normal map, that's good because it is going to configure it for you. If it doesn't, you just need to come here and first of all disable sRGB, because again this looks like color information but it is not, it is positional information, normal map offsets, so you need to deal with that. Next, you need to also take a look at the compression settings. They need to be normal map DXT5 BC5 on DirectX 11, because this is a special type of compression prepared especially for normal maps. So just bear that in mind. Next, we need to know if it is OpenGL, because in the Advanced tab in the Texture section, you have the Flip Green Channel, which just flips the green channel as it says, and that's how you can convert the OpenGL map to DirectX. If you remember correctly, I have already said that this is an OpenGL map, so you can see that if I don't convert it, bumps, instead of being bumps, are valleys, and they displace the normal inwards instead of outwards. So just be careful. I'm going to flip the green channel again, and next we will see it in the normal texture in game so you can see the difference. Okay, so using a normal map is quite simple. You just need to open up the material. In this case, I'm going to open up the complete material, and I will just bring my normal map in, drag and dropping. You can see it right there, and we have a normal ping, and that's the only thing we need to do. Just plug the normal map into the normal ping, and that's that. You can see that detail already appears. We can see it better with a plane here. You can take a look. You can see that we have extra detail. If I unplug the normal map, you can see that it is gone. So that's pretty much it. You just plug it in and it brings the detail. By the way, if I flip the channel, so you can see the effect that it has. Let me just go down to the flip green channel. If you do flip the green channel, you're going to see that bumps look different. Let me get closer so you can see it. And we can do it again. Okay, so you can see that the flip green channel is what we need to do, since remember, this is an OpenGL normal map. And if I do flip it, you can see how it affects the surface. You can see that if I don't flip it, it looks like it goes inward instead of outward, and that's incorrect. So we need to flip the green channel. Maybe you can see it better in here. Take a look at those splashes, those dirt spots, and take a look at how when we flip the green channel, they look like they go inward, which is not correct. It clearly is dirt that is on top of the barrel and it should go outward. So you can see that here everything is looking correctly. This is the only thing that we need to do for the material to take account into the normal map, but I want to show you a defect of the normal map which is quite important. It looks okay from head on, but if you go to the side, since it has no extra geometry, you can see that it is completely gone, the effect. So just bear that in mind, that if you go to extreme angles, the normal maps will not be apparent. Okay, so now that it is in our material, let's go ahead and save the material and check it out in game. Let's go ahead and apply the material instance, and you can see it right there. So you can see that it has a lot more bumps depending on what the normal map is saying, but you can see it right here. If you remember correctly, we had that in the normal map. Let's take a look real quick so you can see it, and you can see that these types of things are what translate into more bumps and the barrel looking way more beaten up and way more old, with a lot of hits that have deformed the metal. So just bear that in mind. It looks way more detailed than it would if it had no normal map, as you can see. I can also disable it so that you can see it real quickly. If I go ahead and disconnect the normal map with Alt-click, and now I save the material, just take a look at the surface. It loses a lot of detail. So that's it for this video. I hope that you know now how to use specular and calculated, how to use ambient occlusion, and also normal maps. As you can see, there were quite a lot of concepts that were not straightforward, and if you didn't get them right, materials would look weird. So be careful and follow the steps that I have laid out for you in this video. I hope this video has been useful to you. If that is the case, go ahead, like and subscribe. If you want to keep on learning about PBR in Unreal Engine, we'll see each other in the next videos.